Okay, let me get started. So the talk is about neuromorphic computing, but I'll try to dig into both parts, the theory and practice. And so the question that I'm going to ask, the big question is this. What do we need to build an artificial neural computer? Now, by that, I mean an actual device, hardware, that does learning in a sense similar to how a biological neural system function, how our brains work. Now, of course, even if it's going to take essential features from how our brains work, it will not resemble, it need not be biological purely. It may still be a physical system, and I'll argue that that is possible. And that is kind of one of the things that we now do in my newly founded company, is actually, building the hardware that will be capable of learning, not just software, but the hardware, and that's what we call an artificial neural computer. If you have questions at any time, just stop me. It's much better to discuss it right away rather than wait until the end of the talk. Okay, so here's a brief outline. 5 steps. I don't know how Dig will be able to dig into each of those 5 components. The first one, I'll just generally talk about neural networks and the type of neural networks from machine learning, physics, and biology points of view. Then I'll talk about how you can have a thermodynamic description of such systems. Then I'll argue, and all those steps will be necessary for me to build necessary conditions for this artificial neural computer, right? And what is it we need to know? And from each of these sections, I will take something and say, well, here's one more thing you need. Here's the second thing you need. The third one will be scale invariance. I argue that's very important for this computer to actually work. And then we'll briefly talk about the design. So we'll discuss what the digital computers are and what's the problem with them, and how you can make a neural computer and what kind of tasks each of them can do, good or bad. And then there'll be a bonus section 5. So I'll argue that there is a possibility that although we'll be just building learning machines, the neural computers that are capable of learning, it may be that they will turn out to be approximately quantum. And if that's the case, then that will be one of the byproducts of all this research and development. Okay, so let's move on to the first, to the first section. Now, before I start developing a theory, I need to form the foundation, mathematical foundation. What do I mean by learning? And the best place to start is machine learning systems. They are where the people are building artificial neural networks and then use them for learning. So let's build this apparatus, and we'll take this apparatus through the entire talk, and we'll be using terms from this slide to when we generalize it to other systems. So since the machine learning system is a dynamical system, if you have a dynamical system, you need to specify 2 things. What are your variables, things that change, and then what is the dynamics? And so in machine learning systems, it is interesting because it has something that we actually don't have in physics very often. It has 2 different types of variables, and those are called trainable and non-trainable variables. Non-trainable are states of neurons, if you're familiar with artificial neural networks. And the neurons can be either in the bulk or in the boundary. We'll discuss that a little bit later. So some of them may be hidden, some of them be on the input-output layers of your network. And that's something we do have in physics. Classical and quantum also physics are formulated exactly that way. We have some states. In classical physics, the variables are variables in the phase space. In quantum physics, variables would be your state vector. But then there is this trainable that I'll talk about shortly. And then there are 3 types of dynamics. There is a boundary dynamics, which is, you may think about some probability distribution of only the boundary neurons, only input-output neurons, like images of, handwritten images of digits. for example, that is input layer, so that there is a distribution of pixels that describes those handwritten images. So that we call boundary dynamics. It may or may not have temporal ordering, not important details at this point. And then there is activation dynamics that takes the state vector and evolves it through the learning system. Now, both of those things we do have in physics, in normal physics. Everybody knows that you need to specify boundary conditions in order to solve for the, let's say, Laplace equation in the bulk. And so that solution of the Laplace equation is, you can think about as a propagating through the network. Basically, you change the boundary conditions, then all of the degrees of freedom in the bulk has to be adjusted. You can think about this as activation dynamics. What we don't have in physics is that those W's and B's, now things that describes your activation dynamics, have life on their own. They evolve according to their own equations, and those are learning. This is what I call learning dynamics. Here is an example of stochastic gradient descent, where the weights and biases change according to this gradient rule. It's called stochastic because you're not averaging over the entire batch, but there is some stochasticity in how you choose the ensemble over which you average before you make your step. Again, not an important technicality. What is important here is that there are these timescales, and the timescales of boundary and activation dynamics are roughly the same. You change the boundary, and through that, the activation dynamics takes this information through the network. And there is another timescale, learning timescales, which is much, much larger. So this is an important distinction. Okay, so this is machine learning. Now let's move on to, and there are references. The first one where this construction is described. Basically, I call it the universal constructions because every type of neural network you can put into this formalism, into this framework. Okay, and there are some other articles. I'll use some of them in later stages of this talk. Now there is a biological learning where, again, we want to use same mathematics, same type of variables and dynamics, but we need to associate what do we mean by trainable and non-trainable variables. In biology, we do have the trainable variables. So here's an example of a genotype, and the non-trainable would be environment and the state of the organisms, as an example. Now, and then what happens is that you change your environment, that changes the boundary condition, and because of the changing environment, the organism reacts and the information gets through. And again, this happens on the same time scales, both boundary and activation, and then in much larger time scales, the organisms learn what is beneficial, what's not, and so they adjust their genotype, and that's called biological evolution, basically. But those time scales are much larger, so very similar in biological learning. Now, our main interest, however, and this is the references for that. And in fact, this is just an example when we discuss biological learning on some scales, but you can go to higher scales where instead of organisms, you talk about groups of organisms, or lower scales where instead of organisms, you can talk about individual cells. And the same split between variables and dynamics can be observed. And so those are the references, but we are here interested in the physical learning. So basically, we want to take a physical system and say, okay, can we design it such that it has everything we want? So as I told you, there is no trainable variables in our usual understanding of how the physical world works. Hamiltonian dynamics with a classical quantum just doesn't have learning, period. And so you really have to play tricks and adjust it somehow to make it seem as if it is learning. So okay. So now, and that's why I highlighted it in red. But here, let me give you an example of when it does happen. I said it doesn't usually happen in physics, but there are some places where something similar happens. So one example is, you can think about, again, Hamiltonian, which is just some fixed machinery that tells you how system evolves, but there are coupling constants in there. And so if you start changing those coupling constants, you effectively change your theory. You're moving in the theory space. And so that would be equivalent to having this learning dynamics. Now the actual Hamiltonian, the actual evolution of the Hamiltonian evolution of the state will change as you adjust those parameters. And here's one example where that does happen. It's gravity, right? So you have a local system. It has a well-described Hamiltonian that describes it, and then out of the blue, a gravitational wave passes by. And so some degrees of freedom pulled further apart, some pulled closer. And so that effect in the effective field theory description, it changes the couplings between them, strength of the couplings, because you've stretched or contracted in a certain way. So gravity, in a sense, has this feature which resembles learning. Now, another thing that is another place where we will see that gravity has features of learning is how it deals with entropy, right? So usually you have in the room, you put all the molecules in a corner, they spread out, the entropy grows. Now this is not what happens with gravitational systems. Gravitational systems try to actually form clusters, clump together. Okay, so this is just an overview of what learning is in all three pictures: machine learning, biological, physical. But the main, and those are the references, but the main takeaway message is that we need this. We need two types of variables, the ones that have very different types of dynamics. One we'll call trainable, others we'll call non-trainable. And that's the first challenge that we're faced if we are to build an actual machine that does thinking at the level of hardware. Any questions at this point? Okay.
No, it's good for me. Thanks.
All right.
If anybody else has questions, I don't know.
Yeah, and it's a small group, so do not hesitate. Just interrupt me. We'll go on.
Since you interrupted yourself now, I mean, in this model, where would you put the genetic component of biological systems?
Yeah, genotype. It's right here. So the trainable variables.
Is that's the genotype?
Yeah.
So trainable. Yeah,
they're like organisms are trying to learn from the environment what is the best behavior, and then the good organisms who train those variables well survive. Now, for a very long time, dinosaurs were very well adjusted to the life on Earth, but then suddenly environment changed, and that's it. They were not good enough and died out. But this process of constantly learning the environment and adjusting is something, sometimes they call this adaptable genes. There's biology is a interesting science on its own, because they may have same labels, different labels for the same phenomena. And it's really, the way when you ask me a question, what is trainable, what's not trainable, I'll have to ask you, what is the time scale you're considering?
Exactly. This is what I meant to say about the time scale, because it seems to that the genetic the genetic code, if you want, is there are some recent studies showing that it can actually change only through your own perception. It's not just the environment or other factors, but
that's learning. That's basically what. So again, we wouldn't have time. It's a separate talk on its own.
Yeah, exactly.
Like many talks, but it's we call it multi-level learning.
Basically. No worries. I'm not going to interrupt. Okay, thank you.
Yeah. It's a multi-level learning. It happens on different levels, on different time scales, and okay. So let's go back to this question, right? So where identified there has to be trainable variables, and the other thing is, if you are to do something with a physical system like condensed matter, soft matter, you need to create a phenomenological description where you do not pay attention to small details. You coarse grain over integrate out some of the degrees of freedom. And the reason for that is because we just cannot afford to keep track of everything, right? This is what modeling is. You pay attention to what is relevant and you integrate out what is irrelevant. And when you do that, you treat these things that you've integrated out at the level of ensembles, statistical ensemble. And when you do that, you are in the realm of thermodynamics. Now, this is basically the statement. Yeah, so in the real thermodynamics. Now, thermodynamics is only one of the physical phenomena, and there are many others that would need to be explained if we are claiming that everything is learning, and the world is a neural network and things like that. Now, so far, this is still work in progress, but at least the first 7, we have a pretty good idea and published work of how things, how does the classical mechanics would emerge from the equation that I gave you on the first slide, right? Not clear. Here we'll pay attention to thermodynamics, self-organized criticality, and then quantum mechanics as a bonus, but I will also may mention how the field theories emerge. The rest is just beyond, again, the scope of this talk. So let's concentrate on the thermodynamics. And as I said, this is where we want to go from micro description of the first slide, where we all had all this equation, to macro description, where we say, all right, let's just coarse grained over some of the degrees of freedom. It is as if you are taking your glasses off, right? So before you had sharp vision of every single thing on your picture, and then it becomes a blurred picture. And that's the technique. This is a technique that we use in physics. And then once you do this coarse graining, things emerge. Different things may emerge. Now, you cannot just say, I think this will emerge, or I think that will emerge. You actually have to do the calculations, showing under which assumptions about your microscopic dynamics, what kind of phenomena, microscopic phenomena will emerge. And so this is one. So let me just tell you a few things that happens with when you start doing. So we already done this 100 years ago for physical systems, where with a Hamiltonian, we describe the Hamiltonian mechanics. Now here, as I said, it's a new type of system. It has something new. It has the learning dynamics. So now we have to redo everything that was done before, but again using the machinery that we have. So it's a new type of dynamics, but we still use machinery of statistical mechanics for that. So one of the things that you notice just by doing experiment is the following. The loss function will go down with evolution. So you are not really here in equilibrium, but then eventually you will get to the equilibrium, and your loss function starts fluctuating around some value. Now, machine learning is called the loss function. Sometimes cost function. In biology, it's actually a log of the fitness. In physics, it turns out to be equivalent to Hamiltonian, to energy function. And we know how important Hamiltonian in constructing both classical mechanics, but also statistical mechanics. It plays the key role because when you construct statistical systems, analyze statistical systems, you construct ensembles. You say, all right, so it's a probability distribution, but what is there that we know about the system? And you say, okay, well, I know the average energy. And if you do that, then Hamiltonian is the thing that you put into the exponent according to the maximum entropy principle. Okay, so here the key role will be played by the loss function. It is some function of the microscopic parameters, but you, and I will denote it with H if I talk to loss function, just like Hamiltonian. Similar to Hamiltonian, it's not Hamiltonian. And you would be describing the average Hamiltonian, like average loss function. And this is what you see, what happens when time goes on. System learns and then tries to minimize its loss. Well, that's fine. Now, in a statistical description, you can also show that temperature-like parameter will decrease. Now, temperature is not some new thing that you have to introduce. It is actually the inverse of the Lagrange multiplier that imposes a constraint on the system. And the constraint is on the average loss, like I said. So it has a precise value. So all this is clear. And then you see this, the entropy is also decreasing. Okay, so now you look at all this and said you had a closed system. It was a learning system, closed in a sense of everything was, its dynamics was completely determined by the dynamical laws. Not closed in a sense of being a physical system, because it isn't a physical system, it's a learning system. Okay, and what you see is the entropy is decreasing. So very interesting, because we usually don't have systems in physics. We do not think in physics that entropy can decrease. If it does, then it's something weird, and maybe it is we're moving to the realm of biology, or at least we are at the boundary between physics and biology. And the reason for that, I'm as a cosmologist can tell you, it just doesn't make sense for, now why would I believe that entropy can decrease? Because in physics, if you wait long enough, the system will just explore all of the phase space, and basically the states of low entropy will be exponentially suppressed. So, and then I would have, if I am in a universe described by physics only, no learning, then my conclusion should be, well, I have to be a Boltzmann brain. This is the easiest explanation of what I have, because out of this thermal death, having all those unnecessary planets and a sun emerge is just it will take too much time. It's much easier for me to just be a brain hallucinating about everything, including this meeting. Okay, so that's not good. And so the claim here is that really something's missing. And so we are saying, well, what's missing is this a feature of learning that you can actually experimentally observe that the entropy doesn't increase. And then this brings us to two new laws of thermodynamics of learning. So it's not the classical thermodynamics, although they're similar to the laws of classical thermodynamics, they're different. So the first law is still similar because it just explains you. First law is nothing but you say, okay, I have of thermodynamics, you have energy, and you say, I want to model energy as a function of extrinsic parameters, intrinsic parameters like entropy, number of particles, etc. And then once you model it, you can write a differential of u with respect to those parameters. So u is a function of s, but then du is the function of something times ds, and then t now has the definition of du ds, right? So derivative. And this is what we usually call a first law, and we're saying that, well, in the equilibrium, if your energy changed, then it must be due to the jump in the entropy. And that's all good. That all makes perfect sense. Now, only here, u is not the energy, but the loss function. And S is not any entropy, entropy of the environment, entropy of the data set. So in machine learning, it's entropy of a data set. In biology, it's entropy of the environment. In physics, it would be entropy of the boundary conditions. So that would be a well-defined thing. But of course, you can add other components here. You can add here entropy of the also bulk states. You can model it as a function of number of neurons. Again, now we are moving completely from the classical thermodynamics to learning thermodynamics. And as you do all this learning, the first law is generalized this way. And then, for example, this will tell you by how much loss function will change this term if I am to add more entropy to your data set, to the environment, or this will tell you how much your entropy, your loss function, will change if I am to add another neuron to the system, or this will tell you how much your loss function will change if I add another trainable variables to the system, so things like that. Okay, this is the first law, and the second law is, and again, it's similar, although now here the loss function need not be minimized with respect to those variables. It can be maximized, minimized, whatever. We only know that this has to be a condition, or this for a simplified system. But the second is very different. The second law is very different. And again, this is something you can observe experimentally. And something I already mentioned is that actually with time, if the dynamics is dominated by learning, then the entropy will be decreasing, not increasing, but decreasing. And those are two main results from this thermodynamic description. Now, how do you get those results? Well, as I said, you have to set up statistical description. You can write down ensembles, define a partition functions, derive all those things, and then say, okay. And then, of course, at the end of the day, test it. And if this is what happens, you are happy with it. Now, note that here I only talk about the entropy of the non-trainable variables. There's also entropy of trainable variables that you can include here, and it will have its own temperature, and the dynamics or coupling between the two is yet another interesting aspect that I won't have time to talk about. Okay, but to summarize everything we discussed so far, and I'll take a question in a second, is that, okay, so we are building this computer. We know that there has to be two types of degrees of freedom. And now we also know that there has to be some degrees of freedom must allow for entropy to decay, to decrease. And this makes us think that most likely has to be a system with a broken ergodicity, where the system actually doesn't explore all of the phase space. It gets stuck in some minimum for a very long time, and then it can go to the other place. So it does not explore everything. Okay, so there was a question, but then the person who wanted to ask a question.
Yeah, sorry. Hi, Vitaly.
Okay. Okay.
First of all,
okay, go ahead.
First of all, thank you for this session. I wanted to ask you. Well, I'm just an IT engineer. I'm just a nerd, not very academical. But can you go back to the previous slide, please? There's something that bugs me. Are we sure that we are allowed to use time in here?
There's no time here, so this is equilibrium action. Oh, you mean for this one?
Yeah.
Well, I mean, it's a law, right? So you plug it in, you measure entropy, you see how it changes, you see it goes up and down. Now, this time is the very same time that we had in the first slide, right? So it's this time. This is time that describes the evolution. So there is a time in which computational learning system evolves. So this is our time. This is not the same time. Maybe you're asking again a question outside of the scope of this talk, but this is not the same time that you would have in general relativity, or the time that you would have in other system. In other places, time may emerge and have a different meaning. Here it is computational time, like CPU time. Boom, boom, boom. Something. Yes, I will go back.
Yeah, what I meant was not really a technical question, but if time is part of the computation,
it's your step, computation step, right?
Yeah, but from the entity that is learning, from his perspective.
Yeah, so from the point of view of this entity which is learning your program, whatever, it makes learning steps once per epoch, like training epoch, whatever, or once every mini batch. So 100 times per epoch. So there is a clear meaning of what time is, and there are different time scales. Actually, times are very important here. Now, so let me just walk you through all the time scales again, because it's important. There is a time scale for individual steps of the activation dynamics. Those are the tiniest one. This is one time you execute activation dynamics. There's another time scale, bigger one. When you on all those time scales, the signal can propagate through the bulk, and now you change your boundary condition, change your data from the data set. This is the second time step scale. The third one is when you do this activation dynamics a few times, and then you do a single step in the learning dynamics. You change your weights and biases a little bit. This is the third time step. The fourth time step is when you actually reach equilibrium. And this is the time step, which is 1 over this alpha. Okay. And so there are many time steps. And now you're asking, where is this relevant? Well, this relevant is when the time scale is very large, you're already in equilibrium. So it's even bigger than the fourth time scale. And when is this equal? Well, it's relevant even when you are not in equilibrium. So, and that's completely analogous to what the first and second laws of thermodynamics are in classical. So
yeah, Vitaly, I was trying to say a different thing, but I understand your passion. I meant we can use time this way if we were outside. Well, we are outside, but I mean, maybe it's just maybe we are saying the entropy is decreasing, but maybe because we are considering time as an entity within a layer that is not allowed to be, because it's higher than the laws we are trying to use in terms of functional meaning.
Yeah, truly speaking, I don't even know what you mean by this. Time is time. We have dynamical system, and in dynamical system there is time, and you use it to model. Now, if you want to have a different definition of time, you do it. And actually, in some of the papers, I do have different definitions of time, but they go beyond, it's gravity. Then you need different time.
Okay.
But here,
I want to bother you. Sorry.
no, that's fine. Okay, so good. So again, we are down to earth people. We are trying to build a machine that can do learning for us. We know that digital computers are not designed for that. And this is what we're doing. Okay, so two things already. Two types of variables. Entropy of some variables must decay. And so this material or whatever it is, it has to have a broken ergodicity. It has to have lots of metastable states. Now, usually, example of such system is called glassy system. So glassy system would be example where you have that. Okay, so moving on now, scale invariance. So it's not enough just to have ergodicity broken. We want to have a scale invariance, and that's again something we obtained from machine learning systems, as I will show you. Now, but as a side note, the criticality or fractals you see everywhere, right? So here are examples where fractals appear in nature, and this is an experiment. And the phenomenology of this experiment is self-organized criticality. So what is that? Well, criticality tells us that at certain places, phases, and certain temperatures, when you tune your parameters, the system goes to the state where the fluctuations are described as a power law, and so this is a critical state. I think I'll talk about this. No, I don't have a formula for that. Because I try to be short here. Okay, so those are critical phenomena. It's only when you fine-tune temperature of a system to be right at the phase transition, then you will see this power law fluctuations, which the numerical experiment tells us it's essential. If you want to have a system that is learning, then learning well, then it has to have some kind of criticality. Okay, so adjusting temperature to a state is one solution, but then there is another one. And there was like a very popular topic, I don't know, 30 years ago. People said, well, certain systems just self-organize themselves to be critical. And SenPy model by Bach and others is first examples, but some other models were developed. So we want to have a critical state. We want a system to be a critical state, and it would be even better if actually it's adjusted itself to be in critical states. So you don't have to fine-tune temperatures. It just goes to that state. And it turns out, interestingly, that just the machine learning task of recognizing handwritten images, this is the famous NIST data set. If you take arbitrary neural network with some bulk and boundary neurons and train on it, then you will see the distribution of fluctuations has the power law behavior. How do I know it's a power law? Well, here I plot the probability of jumps in the weights for some particular chosen weights versus probability of jump versus how big the jump is. So, of course, the large jumps are suppressed, the small jumps are rewarded, but the point here, main point here, is that if you put plot it as log, then you see straight lines. Straight lines on the log means that the distribution of jumps is a power law. And that means that there are some large jumps that are not exponentially suppressed. So if it would not be this, it would mean, like, for example, if it was Gaussian distribution, then this would decay much faster and wouldn't have those long tails. And that's what we see here. If you start training your system in the beginning, it has a Gaussian distribution. So on the log, you do not see a straight line. And eventually, as the system evolves or learns, the jumps in the weights, and the jumps are the adjustments of weights due to learning dynamics, exhibit this power law behavior. Okay, so we know for sure the machine learning systems have to go to this kind of critical state. And so if we are to have a physical system, a neural computer that does the same, it's better have this third component. So here are some derivations, analytical, showing why that happens. Basically, without going into details, the main point why it happens in machine learning systems is because there is this quartic coupling, 2 powers of x, which are non-trainable variables, and 2 powers of q, which are sitting here, which are trainable variables. And because of this quartic coupling, you will see once you do your statistical mechanical analysis and you do the integral of the partition function and then take a log, then you obtain this results, which is telling you that there are 2 parts to the free energy. The one that, and the free energy, think about this as some macroscopic generalization of what's relevant for the canonical ensemble at macroscopic scales. Not the average loss actually, but the free energy, which has both average loss part and the entropy part in it. So anyways, there are 2 components here. One just comes from the beginning, and the second part is the result of this integral that you take here. And the interesting thing about it is that this log becomes a power law-like behavior from the point of view of a probability distribution. And so then you have 2 terms, which is a power law term and exponential term. And you're expecting that for small fluctuations, you'll see the power law behavior, and large fluctuation exponent. Now, it's a horrible explanation for this because really, again, this is a separate talk that I have to give to explain all that. But really, it is explaining you why here you have a straight line and here it curves down as it should be in exponent. Heavy rain now. Okay, so, and that gives us the third component. And again, I'll pause, ask if there are any questions. So what we want from that material or computer, it better have 2 parts to it. It has to have trainable, non-trainable variables, 2 types of variables. It has to have broken ergodicity, so there has to be a lot of metastable states, and it has to be some kind of scaling variable. So this is a bonus, but it would make it actually good learning. If you don't have that, that would be not a learning. Questions so far? Okay. So let me move on. So now we'll go to the actual computer architecture. And see how we can design such a computer. So this is what a classical von Neumann architecture, and this is pretty much the architecture of the computers that you're using right now to connect to this Zoom meeting. There is input, output, whatever the devices used for input and output, like monitor, keyboards, mouse. Then there is a memory, and there is a processor. Now, memory is just internal state of the system, and the processor is predetermined rules of how to change this state. Now, if we are going to rewrite it in terms of what all this means in the language of neural networks, then we really have the input-output, which is what I call the boundary neurons. You have memory, which is what I call the bulk neurons. Both of them are non-trainable. You don't train them in any way. And there is a processor that was pre-programmed to do certain operations. And this is like activation map. You give it in some initial state, you go through one CPU cycle clock, and then it will produce a new state. Okay, so doesn't have learning. So W and B are actually fixed. And so this is a good digital computer. It's good in performing arithmetic calculations like addition, subtraction, division, multiplication, all this, but it's not good in learning. It's not designed for learning because there is no the weights and biases are not treated differently. They're treated the same way. So when you work with artificial neural networks, both the states of neurons and the weights of biases, they kind of recorded in the same place, and so they're treated equivalently. Okay, so here is a generalization that we would want to have. We really want to be able to adjust the processor, so we want to be able to or leave the process as is and have this more fluid processor that we'll call activator, that is able to actually change its own dynamical laws. And the way it changes is from the optimizer. So optimizer will tell you, look, you have this B's and W's adjusted a certain way. And the optimizer knows what is it that it wants to optimize. It knows what is the loss function. And then once the activator got it, then what it takes, there is a trainer that will just keep supplying their different boundary conditions. So its optimizer doesn't just change W's and B's as it wishes. It changes it based on how the trainer, what kind of training data set is being streamed through the activator. So, and if you have those three, then the trainer would be like a training data set. The activator would be exactly the same what the processor was, but now it will have the more fluid or dynamically changing W's and B's. An optimizer will be will be the one who is responsible for changing W's and B's. Now, when I give you this architecture and I put all those train, activator, optimizer, in all three different corners, this is just for illustration. Of course, we at this point don't know what this material should be, and it will maybe just all one block that just does what we want it to do. But it has to do all three. We have to be able to stream the training data, and we want it to be able to change how it reacts to the stream data. Okay, so here is one example of what I think was the best, most promising example of what this material should be from 1 year ago or so, more than that, a few years ago. Now there is more work done on this, and we are working on that very actively. So and that would have to be an additional talk and to describe the condensed matter part of it. What is really the material should be? But here is an example of a system that actually has those three desired components. This is a paper by those authors, and it's called Percolation with Plasticity for Neuromorphic Systems. So they did not envision this as being a processor, neural processor. They thought about this as more like of a memory, but it is good enough for that. As I said, this is not a perfect system, but it's a good example to illustrate how it may be possible. So what happens here, we have a trainer that changes electric potentials at the electrons from some training data set. So you have electrons, and you just stream data. You can here only two, but you can have, of course, a lot more. And that would be how you train the material. And then activator is the currents that flow through this micro wires that exist. And this is all really tiny micro wires. It's like molecular level. And the reason why they flow is because of this word, percolation. If there would be no percolation, there would be no currents. And so for the activator to work, activator part of the dynamic to work, we need percolations. And for the optimizer part of the dynamics to work, we need the plasticity. And what happens is that the currents flow, and then maybe this current is too high, so it burns like a fuse, right? And so there's no more connections, or it starts reconnecting to others. So all those wires can dynamically readjust and change themselves. Again, this is just an illustration, not to tell you that this is really the answer to what the neuromorphic computer should be. Those materials you can check, they're called phase changing materials, and they are really also like this on the right in between, right? I told you the criticality is important to be in between the two phases, and this is seems to be here. And you also see here there are small features and large features, so there's some kind of fractality is already present. Okay, so now we have a few minutes. I want to be done in a few minutes. So we went through all those four things. This is the first three: what the material should be, for what kind of architecture should be. Let's go to the bonus. Again, it might turn out that this is an actual quantum computer once we build it. And again, it's a separate talk that I kind of clumped together because it's supposed to be a colloquial level talk, not a technical. But basically, now you say, all right, so let's think about dynamics of trainable variables on the smaller time scales before they reached on the large time scales, they're really in equilibrium, but what does really happen with them on the smaller time scales? This is still, we are talking about, this evolution here, but let's zoom in and study the dynamics of trainable variables there. So then what you see is that the way you can model it is with the Fokker-Planck equation, which is this one, and then constraints of how the free energy should change. And if you put everything together, then in certain limit you can produce the Schrodinger-like dynamics. Again, I hate to make all those jumps, because the most interesting part is actually, I haven't had time to speak about, is that for this to be true, to actually those two equations to turn into all of a sudden Schrodinger equation, it's not enough to consider your probability distributions. Of course, there are probability distributions, but also to have this free energy, which plays the role of a quantum phase in the state vector. And that would still be not enough for you to produce quantum mechanics. If you kind of take P and F and together you form effective wave function. Why not? Because free energy here is very different. It doesn't have the discreteness, actual periodicity that you would have in a complex phase, right? So if your phase go by 2 pi, it doesn't change anything. Okay, and so what you really get from this considerations, and if you follow a few pages of calculations, is the Mandelung equations. Mandelung equations are not really Schrodinger equations. And to make this final step, to make it a Schrodinger, you have to make an assumption that number of neurons of the system is not fixed, it fluctuates. It can go up by 1, it can go down by 1. And then you get approximately quantum behavior. Okay, so then now I ask the question, what do we need to build an artificial quantum computer? So we really need all of the 3 previous ones, and then we need this mechanisms of producing and moving neurons, or here I call non-trainable degrees of freedom, states of neurons. So if you have all 4 now, of course, I'll be very happy I only have 3, the material with that, then it's already, the learning material, then we can already have hardware that is learning and consuming less energy, faster, it's easy to scale it, etc., etc. But if you also get that, then you would produce approximate quantumness. We call it emergent quantumness. Not the true quantumness. It doesn't mean that this computer will be able to solve all of the quantum algorithms fast, but it will perform certain quantum calculations approximately good enough. And there are some actually numerical experiments that were done. So here an example of the neural network with 4 neurons, no boundary conditions, and everything is fixed other than these 2 biases. And then you follow this neural dynamics of those 4 neurons. And what you're plotting here is how the state at the neuron 1 and 2 changes. And so you see some kind of more or less quasi-periodic behavior, but not completely. So every next step changes. Okay, and then you're saying, all right, can I resemble that through quantum dynamics? This is neural dynamics, but can this be described through the quantum dynamics? And if so, how good? And so basically you do that, and then you end up, so basically you're saying that you have here 2 neurons, and so you can think about them as 2 bits, so qubits or n bits, let's say, for neural bits. And then and then you decide to measure it. And so there are 4 possible states of what you will get from those 4 bits. And then you say, all right, but when I measure, it depends on the time when I measure. And so really the probability distributions evolve. And then I can ask, well, what is there a Hamiltonian that will describe evolution of those 2 qubit system or 2 new bit system? I don't know what you want to call it, but describe it quantum mechanically. And then what you get is that, red is quantum for some Hamiltonian that you can find, and blue is neural. So you see they're pretty close. So for this small system, it was possible to find a quantum Hamiltonian that resembles its evolution. And if it's true, then you say, well, they're just 2 languages. You can talk about in quantum language, and that's one way of describing evolution. And the other one is a neural language, and it's another way of describing evolution. Of course, the 2 are not identical, and you see the blue and red lines are not completely coinciding. That's what I was saying. So you do not produce exact quantumness; you just produce approximate quantumness. Okay, so let me summarize it again. All this is work in progress. Theory is there, experiments are there, and now actually, taking material, and this is what we are doing basically in artificial neural computing, and trying to see how that can be used, what is the right material, and how it should be used to develop this neural computer, because not just material is just a processor. You really need to build everything around it. You have to be able to program it, and if it has emergent quantumness, you have to program an interface so it would seem like you on a quantum computer and things like that. Okay, so this is this is the summary. So let me just leave this slide here. So there are two big initiatives that this one was started half a year ago, and this is what I was talking most to you about, this artificial neural computer. You can find more information on the web. There is a Telegram channel. We run weekly journal clubs where we discuss machine learning theoretical papers. We have a YouTube channel, etc. And this is a new initiative that built out of the very old group, Facebook group of people who just like the idea that the world is a neural network. And if the first part is just mostly physicists, actually, yeah, and physicists, some machine learning people, but mostly physicists. Here, diverse people from diverse backgrounds, and we also have weekly meetings where we discuss what does it mean that the world is a neural network from the point of view of physics, from the point of view of biology, from the point of view of psychology, sociology, and it's kind of less of a more of open-ended discussions, and we'll see how this goes. You can look at again YouTube. There are lots of videos of our meetings, and that's something we just started a month ago, and so we don't know where it will go. So far, it was fun. So, but either if you are interested in what we are doing here, so you can join those places. And if you are interested in this group, you can join the group meetings as well. And now I'll take questions.